Hi, my name is Dr. Deshawn. In this video, we're going to look at the definition of derivative, a topic you would study in a calculus class. Over here, we have the definition of derivative. Once you have a function x, to find the derivative of a function, you take the limit as the delta x goes to 0 of f of x plus delta x minus f of x over delta x, and that provided that the limit does exist. So let's take a look at where this formula comes from, and then we'll look at an example of how it works. So we have a graph of a function over here on the board. This is a function, and there are 2 points plotted on this function. We want to give these 2 points a name. So this first point right here, let's call the x-coordinate x. We'll call the x-coordinate x, and then let's call on the y-axis, its y-coordinate function value. Let's call it f of x, the function value at x, okay? So that means that the name of this point right here, the x-coordinate, we're calling it x, the y-coordinate we will call f of x, okay? So there's the name of this point right here, okay? Now we want to give this point over here a name, so we need a name for the x-coordinate. Well, what is the x-coordinate here? That's going to depend on how far we are away from our given x-coordinate up here. So what do we want to name this? Well, it depends on that distance, doesn't it? Okay, so let me just write some examples in here. Let's pretend that, well, let's say we're 3 units away from this x, okay? So if we're at x here, then where would be, if this distance is 3, where would we be over here? We would be at x plus 3. Would be 3 units beyond x, okay? All right, well, let's, instead of 3 units away, let's say it's 7 units away. So if we're 7 units away, this is at x, where is this going to be? X plus 7, right? Okay, so x plus 7 would be the name of that x-coordinate. All right, well, we don't know what the distance is, so we need to write something to represent the distance between these two x's. So delta x, we're going to use delta x. Delta, Greek letter delta in the mathematics class means a change in something, a difference or a change in something. Right? So we're going to call it delta x, which means we're going to call this point over here the x plus delta x. That would be the x-coordinate. So its corresponding y-coordinate would be the function value, the y-coordinate at x plus delta x. It would be f of x plus delta x. So what is the name of our point right here? Well, the x-coordinate, we'll call it x plus delta x. The y-coordinate is f of x plus delta x. Okay, so here's the name of our 2 points, okay? Now, let's go ahead and draw a line that passes through these 2 points. Here's a line, the green line passes through these 2 points. Anytime you draw a line that passes through 2 points on a curve, that line is called a secant line. Now, what we want to do with this secant line is we're going to compute the slope, okay? So we're going to compute, so we want the slope of the secant line. Okay, so, and I'll just write it in green to correspond to the diagram up there. We want the slope of the secant line. We want the slope. Remember, slope. So to compute the slope, we want to subtract the y-coordinates of the numerator. Remember this? So y sub 2 minus y sub 1 in the numerator. So the y sub 2, so f of x plus delta x, okay, minus y sub 1, which is f of x. Right? Subtract the y-coordinates in the numerator, and then we're going to subtract the x-coordinates in the denominator. So x plus delta x. So x plus delta x for the x sub 2, and then minus x sub 1, okay? All right, so minus x. So we took y2 minus y1 over x sub 2 minus x sub 1, okay? Now from here, do you see in the denominator, we can go ahead and simplify. So we can write the slope of the secant. We can write the slope of the secant in a more simplified form. Your numerator is your f of x plus delta x, all right, minus f of x. And then in the denominator, we can simplify. The x's cancel out, so you just have the delta x left over, all right? So we're right here. This expression over here, not only is it the slope of the secant line in our diagram, but it also has another name. This is called your difference quotient. So this is called a difference quotient, all right? That's used throughout the working with the definition of derivative. This is called our difference quotient, all right? Now, what do we want to do with this? Well, taking a look at our diagram again, if we have 2 points, and you have 2 points, you can find the rate of change in 2 points, which this is essentially, so finding the slope is a rate of change, all right? What if we wanted to find a rate of change at 1 point, okay? okay? So we would if we wanted to find a rate of change at an instant, all right? So let me draw a tangent line to the curve right here. So the red line here is a tangent line to the curve, all right? Intersects, so tangent lines intersect a curve at 1 point. Secant lines intersect a curve at 2 points. A tangent line intersects at 1 point. What if we want to compute the slope of the tangent line? Well, to compute the slope of a line, we need 2 points. Rate of change, rise over run, subtract the y's over subtract the x's. How would you compute the slope at 1 point? How would we find a rate of change at 1 point? So what we need to do here is I drew the tangent line parallel to, has the same slope. Remember, parallel lines have the same slope. So tangent line and secant line I drew, so they're parallel to each other. So what about the slope of this tangent line? Well, if I could take this delta x expression, parallel lines have the same slope, right? So if I can take the delta x expression, if I can bring these 2 points together so they merge together at 1 point, then I can actually write the equation of the tangent line, all right? So what do I want to do? If I want these 2 points to merge together, I need delta x to be 0, don't I? So delta x will if I put 0 in this equation though, gives me a 0 in the denominator. You can't do it, you can't solve that. So what's the next best thing that I can do? Well, instead of substituting 0 in for the delta x, let's see what happens as we approach the delta x, as these points approach the delta x, we come in from the left and the right, as delta x approaches 0 from the left and the right. So to get your slope of the tangent line, so to get the slope of the tangent, all right, that's our red line. So to get the slope of the tangent line, what we want to do is we're going to use the slope of the secant, because I have these set up that they're parallel to each other. So use the expression for the slope of the secant, but we want the delta x to actually go to 0. We want the distance between these 2 points to go to 0. So we want delta x to go to 0. We can achieve that by taking the limit as delta x approaches 0 from the left and the right of our difference quotient expression, f of x plus delta x minus f of x, all right, and then all that goes over delta x, all right. So this expression right here, this is our definition of derivative. This is what it is. This represents a rate of change, slope of a line is rate of change. It represents rate of change at an instant, at a point. So rates of change, you study lots of rates of change when you do applications with their derivatives. So velocity is a rate of change. Velocity change, average velocity is change in position over change in time. But what if you need velocity at an instant? Those are the applications that you will do when you learn the concept behind how derivatives of functions work. Derivatives of a function finds you rate of change at an instant. So here is our expression right here. Important to note, okay, what's important to note is this expression, the slope, okay, of our tangent is the derivative of our function, isn't it? All right, so slope of the tangent line is the derivative of our function. All right, so slope is derivative. Slope, the concept of slope, rate of change, slope is derivative, okay? So for the first example we're going to do, I want you to keep that in mind, okay? So the slope is derivative, okay? So derivative is a rate of change at an instant, okay, on a function. So slope, the rate of change at an instant, and that's what a derivative is, okay? So let's take a look at a linear example in this video. All right, so this is our example we're going to look at. We'll look at a linear example in this video, and then I'll come back in the next video and we'll do some more polynomial and algebraic rational examples. So this one, let's go ahead, we're going to find f prime of x, okay? So f prime of x, that is notation that means derivative. So let's find f prime of x, okay, when for a function, the function we'll call 3x minus 2. So this is a linear function, so we're going to find the derivative of this function, okay? F prime of x is notation for derivative. So how do we find the derivative? Well, the derivative definition, to find the derivative, we're going to take the limit as delta x goes to 0 of f of x plus delta x minus the function all over delta x. This is what we're going to do because this is the definition of derivative. This is what we're going to do. Now let's plug in our functions because we have to evaluate some functions in here. So our derivative is the limit as delta x goes to 0. Okay, so what do we have here in the numerator? F of x plus delta x. Let me put it in grouping symbols here. I want to take my function and replace the x's with x plus delta x. So 3 quantity x plus delta x, quantity minus 2. There's f of x plus delta x. All right? So f of x plus delta x means we're going to take our function and we're going to substitute x plus delta x in for the x's for our functions. There's f of x plus delta x. You subtract from that the function, the entire function here, just bring it down. 3x minus 2 is what the function is. Okay, so 3x minus 2, and then all this goes over delta x. Okay, so you're substituting function notation in, so f of x plus delta x minus the function all over delta x. All right. Once you establish and substitute your functions in here, let's go ahead and expand the numerator. Expand, so multiply out, okay, distribute, all right, distribute, so 3 times x, okay, plus 3 times delta x minus 2, distribute the negative minus 3x, distribute the negative positive 2, all this goes over delta x, okay. Cancel common terms. Let's see what we can cancel here. You have 3x's here, minus 3x, those are gone, okay? So 3x's, take 3x's away, they cancel, all right? We have a negative 2 here, we have a positive 2 here, so negative 2 and positive 2, those are gone, okay? So what do we have? We have f prime of x is equal to the limit as delta x goes to 0 of, what do we have left over? Just 3 delta x, everything else in the numerator canceled over delta x. All right, looks like we can still cancel out, we can cancel the delta x's, okay? So the delta x's cancel, so now our derivative of the function, all right? So the derivative of the function is the limit as delta x goes to 0 of our constant 3. Anytime you take the limit of a constant, your answer is the constant. As the x's go to 0, from the left to right, so delta x's approach 0 from the left to the right. The y's are going to stay right at 3. Anytime you take the limit of a constant, it is that constant. So the derivative of this linear function is 3. The derivative is 3, and there's your answer. Okay. Now to put it in perspective, what was our function that we were dealing with here? To put it in perspective, our function is 3x minus 2. That's what our function is, okay? Now, we can, what is another name for f of x, right? F of x is also, so y equals 3x minus 2. F of x and y equals f of x, right? So this is what our function is. It's a linear function. It's the equation of a line. This is a function in y equals mx plus b form. What's the slope of our line? The slope of our line is 3. That's the slope. What does the derivative of the function tell you? It gives you a rate of change at an instant, but it gives you a rate of change. So, and what did we find here? We found the rate of change. Well, you can tell by looking at it, it's a linear function. The slope is 3. The rate of change is 3. Your linear functions will have a constant slope, all right? So that's always, linear functions have a constant slope. So when you get into your quadratics and polynomials and rational expressions and trig functions and et cetera, that you're going to have to work with, you know, finding the equation, the rate of change, because if you have a curve, it's not going to be constant. So this is our definition of derivative, okay? It's where it comes from, what it represents. It's a rate of change at an instant of a function. Okay, and here's our first example, linear example. I'll be back in another video to demonstrate some more examples if it might help. Look for those. So thank you so much for watching. Appreciate you being here. Best wishes, best luck to you. Thank you.